Okay, welcome back everyone. So now we're going to start what's going to be our last session on the research track, which consists of three talks. These sort of be summarized as say like general secure computation, where we're going to hear about different things from trust execution environments over MPC to FAG. Kicking off this session will be Oana from Malta, and she'll be discussing how we can sort of improve security and validity rollups using trusted execution environments. So, big applause for Oana.
Yeah, thank you for the introduction. I'm Oana. Yeah, I'm still Oana, and my talk is about improving ZK-Rollup Security with TUs. To start off the presentation, I'll introduce TUs. So trusted execution environments are hardware enclave that protect the memory of the enclave by encryption. So the memory of the enclave is encrypted, and that prevents any sort of entity from accessing the data and code that's stored inside the enclave, and thus we achieve code and data integrity and private execution. And in addition to that, remote attestation is something that's also very important for TEs. That's basically the process that allows an enclave to prove its authenticity. So any remote party can request an enclave to provide a remote attestation document, and this attestation document links the enclave all the way to the TE manufacturer, proving its identity. So there are a couple of vendor implementations from Intel, AMD, AWS, ARM, and so on. Okay, so at Automata we use TEs to implement coprocessors as one use case. So today coprocessors are very important for blockchains because the blockchain computation is constrained. For example, if you take Ethereum, you have a block every 12 seconds, and each block has at most 30 million gas worth of computation. So that's very small actually, and also smart contracts have restrictions, limitations in terms of how much memory they can have, and there's no floating point arithmetic and so on. So it's a bit out of the question to implement some complex applications such as low latency gaming or machine learning models or outside on the blockchain. So that's where off-chain computation comes into place. The problem is that once we move the computation off-chain, how do we still maintain the decentralization and trustlessness properties of the blockchain? And this is exactly what coprocessors do, because they don't only do the computation off-chain, but they also provide a proof that the computation was performed according to some standards. For example, everyone's favorite coprocessor is the ZK coprocessor that will produce a zero-knowledge proof to show that, hey, this is the computation that this computation actually happened. And as an alternative to that, we build TE coprocessors because TEs are fast, cheap, and very practical. So, for example, ZK is very powerful, but also very complex and very expensive to perform. Okay, so one use case of the coprocessor is the multi-prover. Again, coming back to ZK systems, they are very complex, and also very new. There are new proving systems, schemes, tools coming out every day, and to improve the state of the art, but that means there are very few people who actually know what's happening and are able to go and audit the code to check if there are bugs, and also the developer tools are being created. So because of this, ZK-Rollups are still in the training wheels stages, and it's very important that we make sure we don't allow the ZK-Rollup to prove wrong statements. So for example, if I am allowed to prove that I transferred a token to both Alex and Bob, then you have double spending and the system itself will accept it. And of course, we don't want that. So one way to increase the confidence we have in the ZK-Rollup is what we usually do, namely we add redundancy. We have the ZK prover that will produce a ZK proof as part of the rollup, and in addition to that we have other types of provers that will also produce a proof, and then we check that the ZK proof and the other proof are the same, and if they are the same, then we can sleep better at night that okay, maybe the ZK-Rollup is doing what it's supposed to do. And what we implemented is a TE prover. This prover produces a proof of execution by re-executing the L2 blocks and checking and producing the state transition. So our TE prover is implemented using Intel SGX. So we use Intel SGX as root of trust. Intel SGX is very performant, but we also try to do our best with the code to make sure that the computational footprint is not very big. And as I mentioned before, TEs come with this remote attestation capability. So basically we prove that the TE prover is indeed running inside the TE by also having this remote attestation document that is presented with the computation. So the first the first TE prover that we implemented was for Scroll ZK-Rollup. In that case, we used the Sputnik VM as the EVM interpreter. The prover supports both SGX and non-SGX builds, and by comparing the two, we determined that the performance of the SGX build is less than 10%. And currently, this prover runs both on the testnet and the mainnet, and has agreed so far with what ZK prover, the Scroll prover, computed. In addition to the Scroll prover, which is open source, we also have a TE prover for Linea. They are both open source, and we are working with other rollups to do TE provers for them. It's actually not only ZK-Rollups that can benefit from the TE prover. Optimistic rollups can also take advantage of this, for example, for reducing the risk associated with malicious fraud proofs. So we can constrain who can submit the fraud proof using the TE. And in addition to the TE prover code, we also open sourced our Intel SGX DCAP attestation contract that basically verifies on chain that the TE prover is running on a genuine Intel SGX machine. And lastly, I would like to talk about the multi-prover ABS that we are developing. So currently the TE can prove the correctness of execution, but it cannot prove the liveness. So if, let's say, the TE operators decide that they want to cut the TE from the network, then there's nothing we can do against that. So what the ABS ensures so the ABS will add crypto economic security to the existing TE guarantees. And that means that if the TE operator suddenly decides I don't want to have this TE on the network anymore, then that operator will be slashed. And by having this crypto economic security, we can have new applications for TE. For example, we can implement a very low latency rollup that will use the TE to compute the safe transition. And in addition to that, we are also working on these TE committees. So instead of having a single TE that produces the proof of execution, as it is now with Intel, we can have a committee made of multiple TE vendors, such as, let's say, Intel, SGX, NVIDIA, and AWS. And now all these systems have to agree in order to produce a proof of execution. So this has two advantages. One is that we don't rely solely on Intel, so we increase the decentralization. But also because we need all these technologies, all these three implementations to agree on a result. That means that the potential attacker would have to break not only Intel SGX, but NVIDIA and AWS as well. So we increase security. And this is roughly the architecture of the multi-prover ABS. We have the operators that run their own, that run different implementations of TEs, and then the multi-prover ABS itself that contains the AWS contracts that take care of slashing, rewarding, and so on, and also the attestation layer that makes sure that the proof of execution is coming from a genuine TE. And on the right, we have this thing called reproducible builds. Basically, this ensures that whatever software is running on the ABS, for example, the TE prover for scroll, this code, this binary is produced from the correct source code. This is what reproducible builds does. Ensures that the binary corresponds to a specific source code, and by doing this, we deal with the supply chain attacks. Currently, we have about 41,000 stakers staking to 73 operators with a total worth of restake ETH of 1.74 million. That means all this restake ETH is used to secure any rollup that, for example, involves in having a multi-prover ABS. Here are some links if you want to learn more, and I think that's pretty much it. I'm happy to take questions.
Okay, thank you, Oana. Do we have any questions?
I just have a general question on the roadmap, because at least from my perspective right now, the system seems to diverge. You have so many different implementations of TEs, so many different trust models, because they're just different in how they're implemented, so different TEs. Do you think you're going to come to a point where everything converges in a single system that works as one, or do you think it's going to be different subsystems that just fulfill the same task?
I mean, for one, do you even want them to converge? Because then if all of them converge, then you have a single point of failure, right? So you don't really want that. But there are some efforts to have this TE standardization, like open source and all that. So maybe that could be a source of universal standard. But I personally think that having multiple implementation is a feature, not a bug.
Any more questions?
About the first part of the talk, where you mentioned reinforcing ZK-Rollup security with TEs, Do you think that's something that'll be long-term necessary, or only short-term while ZK implementations are not as battle tested yet?
I think it depends. Like if you have your ZK-Rollup and then it's set into stone and you never make any amendments to it, then yeah, maybe like if it worked for 10 years. I don't know. I think you always want like this defensive in-depth kind of thing, to be honest. But I guess it depends on people what they do safely. But like, yeah, I think it's always better to have an additional layer.
Thanks. Okay, then thank you very much, Oana. One more applause.